Okay, so let's continue our discussion on linear regression using least squares and ridge regression techniques. So to refresh our memories, we're working with a data set that is of the form that comes in pairs. So we have xi, yi for I equals 1 to n, so n observations. The data x is in Rd, and the response y is in R. And we're going to assume that we don't need the bias dimension in x, so we've standardized the data in some way so that we can work without the bias. Really, in the discussion that I'm going to have in this lecture, whether the bias is there or not, it doesn't really impact the math, but it will impact the results that you have. So I'm more interested in discussing the math techniques here. So we're going to use a model of the form y approximately equal to some function of its covariate vector x and some model parameter vector w. So this is very generic. And in particular, we're going to focus on the function where f evaluated at an x and w pair is just the dot product between x and w. So we're making predictions that y should be approximately equal to the dot product between x and w. So this is the function that we want to use, and now we want to learn this function. We want to, by that we mean we want to learn the vector w. And so we do this by minimizing some sort of a loss function that tells us what are good values of w and what are bad values of w. And so we've already discussed a few loss functions. The one that we're going to talk about now or focus on is the ridge regression, corresponds to the ridge regression loss function, also called L2 regularized least squares. So we have as the first term the sum of the squared errors, and as the second term we add a penalty of the squared magnitude of the vector w times some regularization parameter lambda that we set. And so we focused on two examples. One is where lambda is equal to 0, in which case we only have the sum of squared errors. That's least squares. And when lambda is greater than 0, solving or minimizing this objective function gives the ridge regression solution.